Lecture number 4, Magnetic Flux, Permeability and Reluctance, and Inductors. Basic terms and definitions. In this lecture, we omit the fundamental magnetic field theory and focus our attention on the practical terms, definitions, and equations which are necessary for switching power supply designers. We use the International System of Units, and the following table shows conventional units and parameters used in this lecture. Basic definitions and equations. In this lecture, for a better understanding, we have chosen the toroidal coil for further explanations. However, all the terms and equations used here are valid for every shape of the core. Primary definitions and equations based on Maxwell's fundamental equations are highlighted in green. The important parameters we will discuss today are effective area, which is approximately the cross-section area of the core, effective length, which is approximately related to the average radius, the effective volume, which is the effective area times the effective length, mu r, the core material permeability, and n, the number of turns. By definition, the flux density B is proportional to magnetic field strength H. Magnetic field strength is a fundamental parameter that defines the intensity of the magnetic field surrounding any current-carrying wire or group of wires. The equations of the magnetic field strength are quite simple and are shown below. Magnetic field strength is proportional to the total current and the number of turns, and inversely proportional to the effective length. Basic formulae and equations. The magnetic flux phi in the core is a bit similar to the electrical current in the conductor. It flows through the core and has the same value in any cross-section of the core. Due to the circular nature of the magnetic field, the magnetic flux loop is always closed and cannot be altered or interrupted along the way. Phi is the flux in the core, that is, flux through each turn of the coil separately, not through the entire coil. The entire coil flux is n times greater. When the external voltage V is applied between the ends of the coil containing n turns, the magnetic flux begins to grow in the core. This phenomenon is bidirectional, that is, the change of magnetic flux in the core induces a voltage between the ends of the coil. The corresponding differential equation is shown below. And at zero initial conditions, the solution for phi is V times T over N, and the corresponding solution for B is also shown. It is important that the flux and flux density here are independent of the magnetic properties of the core. The magnetic field is a real substance, having both energy and mass. Each volume of space filled by a magnetic field contains energy, which is derived below. Magnetic circuits. Now let's go to the magnetic circuits. Using equations 2 and 3, we obtain an expression for phi in terms of a variable s, where s is defined in expression number 8. Product I times N is known as magnetomotive force, MMF, similar to the electromotive force, EMF, and S is known as reluctance or magnetic resistance. Thus, we can write phi as mmf over reluctance, and we can draw a parallel with electrical circuits where current equals EMF over resistance. The magnetic core may have segments that have different permeability. In this case, the summation of reluctance is similar to the summation of resistance in the electrical circuit. Like resistors, reluctances can be connected either in series or in parallel. If the cord has more than one magnetic path, we have a parallel connection of the reluctances. Now, the total circuit reluctance is found the same way as total parallel resistance. Magnetic circuits examples. Effective permeability. Example number 1. A toroidal core with an air gap. The air gap effective width is delta. Note that this effective gap width is lower than its physical size. Use equation number 8 to calculate the air gap reluctance S1 separately. The solution to this example is shown below. Since the air permeability is unity, the gap reluctance S1 is related to the effective gap width and the effective area, and the reluctance of the rest of the core is related to the effective length minus the gap width, the effective area, and the magnetic permeability of the core, which is non-unity. The total reluctance can be found as the sum of S1 and S2. And because delta is much smaller than the effective length, the expression for total reluctance can be simplified. As the typical value of μr is about 2000, most of the total reluctance is concentrated in the air gap. Suppose now that we have two cores of the same form and the same reluctance. The first core has a very high permeability μr and an effective air gap delta. The second one has no air gap, but its permeability μe is artificially reduced to match the reluctance of the first core. This equivalent permeability μe is an effective permeability of the first core with the air gap. The corresponding equations are shown below. The expression for effective permeability can be simplified if the following condition holds true. In practice, the effective permeability is the effective length over delta. Example number 2. The E-core set. The E-core set has two identical magnetic loops, here and here, and as a result, two related reluctances in parallel, S1 and S2. So, the total core reluctance is found as the parallel connection of S1 and S2. But since S1 is equal to S2, the total reluctance is simply S1 over 2. Inductance and inductor definitions. Now, let's define the coil inductance. In the first step, we find a relation between the magnetic flux through all the coil turns and the coil in the current. Using equation 9, we multiply both sides by n. So, the total flux in the coil is proportional to the coil current. By definition, the proportionality constant is the inductance L of the coil. Thus, L is n squared over S. Inductance is proportional to the number of turns squared and inversely proportional to the reluctance of the core. There is another way to determine inductance. In the magnetic core datasheets, you can find the parameter A sub L, which is the inductance factor. This is a reciprocal of reluctance, and thus, inductance is A sub L times N squared. An inductor is a device with inductance. It is usually a core with a coil. See the gallery to the right. Now let's figure out the energy stored in the inductor. Using equations 3, 7, and 9, we get an expression for energy, which is L times I squared over 2. Now suppose the external voltage source V is applied to the inductor. Similar to expression 6, we get I equals V times T over L. Thank you for watching. The next lecture is devoted to magnetic materials. Please comment or email us with questions.